Good morning, all. In this lecture, we were actually yesterday also we were doing some infinite series. Today also I'm going to continue with this infinite series as a topic. This is an important topic for your exam, specifically for TIFR and JEST exam. Okay. Uh, with regards to CSIR net, I may say that there may be asked a few more questions, but overall, I mean this is an important section that we should be actually looking at. Okay, so let us begin without wasting the time. Okay, so yesterday a little bit of revision that I need to before I start, I should give you infinite series. As a physicist, we are actually concerned with the convergence and divergence of this particular series. Okay, um, even in mathematics also, most often the questions are asked regards convergence and divergence also. But what is the difference between a mathematical understanding and a physics person's understanding? For physics person, we should be able to understand. Okay, this is the series. How would it behave? This is the series. How would it behave? Basically, we need to understand a few series and understand their behavior, and then we can use some tests that I'll write today, and only that understanding would be enough with regards to exam. Okay, we are not going to do much of it, but a little bit of understanding we do. Okay, so yesterday when I started with this particular topic, I told you that instead of seeing infinite series, just see the sequence of partial sum. And what is sequence of partial sum? Let us say I'm saying summation 1 over n is divergent. What does it mean? Actually, the sequence of partial sum underlying this would be 1, then 1 plus 1 by 2, then 1 plus 1 by 2 plus 1 by 3. S4 would be 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. Usually students get confused and they say that 1 over n is the sequence. No, that is not the sequence. The sequence of partial sum for this particular series would be this. And yesterday I told you the convergence of series it depends upon the convergence and divergence of the SOPs. So the series behaves the same way as the SOPs does. SOPs means sequence of partial sum. So basically I have abbreviated this particular thing. as SOPs. Okay. A few series that we actually another thing that I mentioned was, if a series is absolutely convergent, then series is convergent. That is, if at all you're not able to prove what would be anything about some series, just take an absolute of it. Just take the absolute of its general term, and once you take the absolute, and then if you can make some assertion that this particular series, let's say sin n upon 1 over n square, if let's say if I take a modulus of it, I can say that modulus of sin n is 1 is always less than equal to 1. I know this is convergent. So if the larger series is convergent, then the terms with all these terms, like if I take a modulus of it, I can write that sin n ka mod upon n square would be less than equal to 1 upon n square. If this is convergent, then this is convergent. This is by comparison test. Even if you don't understand comparison test right now, just think, if each of the terms, if I compare, and I'm saying this larger series is convergent, then obviously this would be convergent. Why would it not be convergent? So if I just add summation here, let us say the value is pi square over 6, then obviously this value would also be pi square over 6 or less than pi square over 6. So basically this will be convergent. So at times this becomes very handy argument. That is why I just gave you that if series is absolutely convergent, then it is convergent. Then next, in this particular section, I taught you geometric series. With regards to geometric series, just remember that if the common ratio modulus is less than 1, only then the geometric series is convergent. If the modulus R is less than 1, only then your geometric series is convergent. Now, today and then I also taught you one more thing. I think there was another thing that I taught you. Then we went on to telescopic series, and actually did a few more questions there. So like this series, you just try to do it in partial fraction. Always remember that don't just start cutting in every nonsense direction. Don't do that. Just have patience and understand what is the cutting pattern. Because if you just start cutting randomly, then you will miss the pattern. Don't do that. And once you miss the pattern, then there is no turning back. Then you are not going to ever understand what has happened. This is yet another question that I did yesterday, and so and then we also discussed the harmonic series. See, always remember, this harmonic series usually appears to physicists as if that this is convergent. This is not convergent. Okay, so initially when we are trained, actually we think that okay, why it is not the case, 1 upon n tending to infinity, it should be 0, why it is giving us a problem. So don't focus on this, focus on the sequence of partial sum. You can see that the sequence of partial sum is unbounded. It is going towards infinity. See, if I just say, if I just write this summation 1 upon n as 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 plus 1 by 9 dash 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 1 by 16. What I found, I just took this particular thing as it is and I just tried to make a pair here. So 1 by 3 plus 1 by 4 can always be written greater than 1 by 4 plus 1 by 4. Similarly, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 can always be written as 1 plus 1 by 2 and remaining all those things. So in any case, I developed an idea that Sn, the sequence of partial sum in general, is greater than n plus 1 by 2. And if it is going towards infinity, as n tends to infinity, this is also going towards infinity. So sequence of partial sum is divergent, so series is divergent. Always remember, this is an important, you can say, assertion here. Okay, incidentally, now let us come to some of the theorems. Okay, one of the theorems that I need to tell you, what you can say, test you can say, not theorems in general. Okay, let us first understand one of the important result first. And then I'll come back to this harmonic series once all over again. So it says that if summation an is convergent, if summation an is convergent, then always remember limit an would be equals to 0. Then always remember limit an would be equal to 0. Always remember. Okay, converse not true. Always remember converse is not true. This is something that I'm not going to derive, but converse not true. But what freedom that converse not true. Example, summation 1 upon n. So you know that limit n tends to infinity, 1 upon n is simply 0, but summation 1 upon n is not. Okay, but if summation an is convergent, then limit an is 0. What freedom does it give to us? See, for example, in mathematics, whenever we say that statement P is correct and it implies Q, then not of Q implies not of P. What do I want to say? Let me just make you understand it by this way. I am asking you, let's say, give me the answer of summation n. You can straightway say that this is divergent. Why this is divergent? Because the limit of n is equals to plus infinity. So if the limit of an is not 0, then the series cannot be convergent. Okay, so this is straightway you can write this thing. You don't have to go here and there. Straightway you can say this. Is that clear or not clear? Please let me know. And please, if at all it is possible, please remain responsive on chat so that I may be able to understand whether you are getting it or you are not getting it. So that would help me anyway. So remember this one thing, that whenever I'm talking of a series, infinite series, summation an, and if summation an is convergent, then always remember that limit an would be 0. If limit an is non-zero, then summation an will not be convergent. I hope it is clear. Okay. Now let us do some of the tests at first. And once we do the test, then you will be able to do questions of the exam also. Okay. Now let us do some test. So some important test. So one of the important tests is called as the comparison test, and this will solve much of your problem. In life, comparison will give you misery, but in mathematics, comparison will give you answer. Okay, so let us do this particular thing. Okay, so what does it say? It says that let an and bn, sorry, let an and bn, a summation an and summation bn be two convergence series, be two convergence series. Let summation an and summation bn be two convergence series of non-negative reals, that is positive term series I'm talking, non-negative reals. Assume that an is less than equal to bn. Assume that an is less than equal to bn for all n. Then what does it say? It says that if summation bn is convergent, if summation bn is convergent, it implies summation an is convergent. And it also says that if summation an is divergent, then summation bn is divergent. This is an important thing that you should remember. This is very important series. I mean, this is very important test. Okay, if at all only bn is a positive term series, only summation bn is a positive term series and an is not, and let's say an is not, then what you can do, just try to take the modulus of an. If it so happens that modulus of an is less than bn, then it is fine. Then if summation bn is convergent, then summation an nahi, summation modulus of an would be convergent. Then summation modulus of an is convergent. And if summation modulus of an is convergent, that is summation an is absolutely convergent, then summation an is convergent. You have to remember this. Okay, so this is one thing that I wanted to tell you. Now let us come to one of the series which is called as a Riemann zeta function, and I'll give you two treatments to this. The same thing I'm going to give you two treatments. So let us first concentrate on Riemann zeta function. I'm writing here Riemann zeta function. So Riemann zeta function is given by zeta p is equals to summation n equals to 1 to infinity, and this is n raised to power minus of p. Okay, so this is called as Riemann zeta function. Now this particular Riemann zeta function converges if p is only greater than 1. If p is equal to 1, then this Riemann zeta function would be nothing but it would be a harmonic series. And for p less than 1, it will be divergent. Less than 1, it is divergent, and harmonic series we yesterday discussed, this is divergent. So Riemann zeta function, whether you write this way or you can also say this series as harmonic p series. Harmonic p series. This is one of the important series. You should remember this, that if p lies between 0 and 1, then this is divergent. If p is equal to 1, then it is again divergent. If p greater than 1, it is convergent. If you want to understand, I can make you understand. If you want to remember it, you can remember it. But I would insist that you should understand this particular series, only this series. I'm not going to derive each and every series, but let's just try to sketch a proof. I'm not even giving you the entire proof, but let us try to sketch some proof so that at least you get some firm understanding of what I'm doing. Okay, so let us consider the case for the convergence. Let's say if p is greater than 1. If p is greater than 1, then you see I can write this series as 1 plus 1 upon 2 ki power p plus 1 upon 3 ki power p plus 1 upon 4 ki power p plus 1 upon 5 ki power p plus 1 upon 6 ki power p plus 1 upon 7 ki power p, then 1 upon 8 ki power p dash 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 1 upon 15 ki power p, so on and so forth. So what will happen? What I would do, I would simply take these two things in one. So I will simply take these two things in one. So basically what I'll do, I'll simply take these two in one bracket. I'll take these four things in one bracket. So not these four brackets. I would take these four brackets in. I will take these 8 terms in one bracket, and so on and so forth. I hope it is clear. I know that if I want to compare this, let's say I want to just take this. So it will be less than 1 upon 2 ki power p plus 1 upon 2 ki power p. Should I explain it? See, p is already greater than 1. P is already greater than 1. And see, here it is 1 upon 2 ki power p, and here it is 1 upon 3 ki power p. Obviously, 1 upon 3 ki power p is, I'm dividing it by more. So if I compare, this is fine. Till now, it is fine. But now, if I, instead of writing 1 upon 3 ki power p, if I write 1 upon 2 ki power p, this would be greater now, because I'm dividing by lesser term, lesser thing. Is that clear? Only Anurag is there today. Whosoever is live, please let me know. Is that clear? Not clear. So similarly, I will write that this would be less than 1 upon 4 ki power p plus 1 upon 4 ki power p plus 1 upon 4 ki power p plus 1 upon 4 ki power p. Similarly, I will write this will be less than 1 upon 8 ki power p plus 1 upon 8 ki power p dash 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 1 upon 8 ki power p. And what does it yield me? It yields me that all of these things, there is a 1 added also to it, 1 plus. So 1 plus something. This is less 2 upon 2 ki power p. This is 4 upon 4 ki power p. This is 8 upon 8 ki power p, so on and so forth. Or in other terms, I can also write it in this fashion, that this for p greater than 1, the given series that I was calculating, series I was calculating, let's say I'll write it 1 plus 1 upon p, 1 upon 2 ki power p plus 1 upon 3 ki power p dash 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 is less than 1 plus 2 upon 2 ki power p raised to power 1 plus 2 upon 2 ki power p raised to power 2 plus 2 upon 2 ki power p raised to power 3, so on and so forth. Or in other words, I can say this particular series that I'm talking about, whose convergence I'm talking about for all p greater than 1, is less than summation 2 upon 2 ki power p raised to power k varies from 0 to infinity. What do you think this particular series is? Don't you think that this particular series is a geometric series? And it is convergent only if 2 upon 2 ki power p is less than 1, which implies 2 ki power p is greater than 2, and which implies p should be greater than 1. So if p is greater than 1, then this is convergent, which indeed is the case that we are discussing. So if p is greater than 1, then by comparison test, if this series is convergent, then this particular series is convergent. So a Riemann zeta function, which is given by summation n raised to power minus of p, zeta p, sorry, is equals to n equals to 1 to infinity. This is convergent if p is greater than 1. P equals to 1 we discussed yesterday only, the harmonic series. Is that clear? And if I want to write about this, see, what happens if p lies between 0 and 1? What happens if p lies between 0 and 1? Just pay attention to what I'm saying. 1 plus 1 upon 2 ki power p plus 1 upon 3 ki power p dash 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 1 upon n ki power p. Is it not greater than 1 upon n ki power p plus 1 upon n ki power p plus 1 upon n ki power p dash 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 1 upon n ki power p? Let me write all this way. So this is greater than, let's see, 1 upon 1 ki power p. Let me write it here. So basically this is greater than n into 1 upon n ki power p, or it implies that Sn, that sequence of partial sum Sn, is greater than n raised to power 1 minus p. Now if my p lies between 0 and 1, 1 minus p would again lie between what? Again it will lie between 0 and 1 only. If my p lies between 0 and 1, 1 minus p also lies between 0 and 1. So this lies between 0 and 1. This is on this power. Now if I take n tends to infinity, my Sn would also go to infinity. And if my sequence of partial sum is divergent, then the series is divergent. So always remember, n ki power minus p, n equals to 1 to infinity, is divergent for the case p lying between 0 and 1. Is that clear? So this is divergent for the case P lies between 0 and 2. Always remember, this is an important series. This is called as the Riemann zeta function. Okay, this is called as the Riemann zeta function. So I just helped you with the derivation so that you must be able to understand how to apply this, what you can say, comparison test. I hope it is clear. Now, a few more tests that you should remember. Another test is called as the limit comparison test. Limit comparison test, LCT, limit comparison test. I'm writing it here, limit. I don't want to take this topic beyond 2 classes or 3 classes. I just want to finish it today. Just have an understanding of all these things. Don't think that each and everything you have to do much amount of practice. No. Just I'll let you know about the questions also, and then you will be able to see that the questions are not that difficult. Okay, we'll see the questions also for the exam. So limit comparison test, what does it say? It says that let Bn be greater than 0. And if An upon Bn, they converge to a limit L which is greater than 0, then both summation An and summation Bn converge or diverge together. Both summation An and summation Bn converge or diverge together. Both summation An and summation Bn converge and diverge together. This is an important concept, and I'll show you its utility. Don't worry, I'll show you its utility also. This is called as a limit comparison test. Another test that you should keep in mind is called as the Cauchy's integral test. It is called as the Cauchy's integral test, and this is another important test. And two more tests I'll write, and I think that would be enough. That would be enough for you. I think for physics people it will be enough. Another test is called as the Cauchy's integral test. And what does it say? It says that if you want to find if you want to find the convergence and divergence of series, replace it by an integral. Replace it by an integral. So instead of finding summation, try to find an integral. Try to find an integral. So let me just show you by an example also its utility. Okay, so let us say that I want to explore the convergence of, let's say, summation An, and let's say this summation An can be expressed as some function. Let us say that this summation An can be represented as some function. I'll let you know what I'm trying to do, what I'm trying to explain. Let us say I'm talking about summation 1 upon n. So can I not write it as summation f of n, where f of x is simply equals to 1 over x? It is one and the same thing. So instead of doing summation an, just think that you are doing some summation fn, where fn is a decreasing function. Fx must be a decreasing function. This is where this particular Cauchy's integral test can be valid. So for the Cauchy's integral test would be valid. The limit comparison test is easy. I'll let you know. I'll let through questions only we'll understand this. Okay. So f of n must be a decreasing function at first. This is first thing, that f of x must be a decreasing function, and secondly, you should understand that this is one. If this is a decreasing function, then what to do? Then instead of finding this summation, try to find an integration. Instead of finding summation, try to find an integration. That is, instead of, if I'm doing this summation n, instead just replace it by summation fn and just try to find this integration 1 to infinity ft dt. If this is convergent, then summation an is also convergent. So if this integral is convergent, then summation an is also convergent. And if summation an is divergent, then obviously this is divergent, which indeed is not our objective. Our objective is convergence. So just replace this summation 1 upon n summation an by an integration. If this integration is convergent, then this summation an is convergent. Let me help you with an example and then you will be able to understand. The only criteria is that this function fx must be a continuous and a decreasing function. This must be a function must be continuous as well as decreasing. If it is continuous as well as decreasing, then you can do this. So let us let me explain you by Riemann zeta function only. So let us again where is the pen? Okay. So let me again try to write the Riemann zeta function. Let me again write the Riemann zeta function. Again, what is the Riemann zeta function? This is summation n equals to 1 to infinity n ki power minus of p. Okay, this is your Riemann zeta function. Now let us try to do a few cases first. So let us do the simplest case. Let us try to do if p is equal to 1. So if p is equal to 1, I can write this particular function as 1 upon n. So I will replace it by summation 1 upon fn. So basically your function f of x is what? F of x is simply 1 upon x. Now what I told, if this integration 1 to infinity f of x dx or f of t dt, whatever, if this is convergent, then your this is convergent, right or wrong? Okay, and if this is divergent, then summation an is divergent. Okay, so what we are doing, we are actually replacing this by integration. Now let us see what you can say about this. So if I integrate this 1 to infinity, f of x would be what? 1 upon x dx. This will be integration 1 to infinity, and this will be, I think, 1 upon x integration is simply log of x. And you know that log of infinity is infinity, and log of 1 is what? 0. So it will give you log tending to infinity, and which is actually infinity. So basically, if I'm doing summation 1 upon n, this is divergent. This is divergent even from the Cauchy's integral test also. Please let me know if something you are not able to follow. This is an important test. So I'm waiting for the remarks. If there is some issue that you're not getting it, please let me know. And then there are two tests. One is called as the ratio test, another one is called as the root test, and then we are done. Then we'll do the problem solving. Please let me know if there is something that you're not following. So probably we'll take one small class tomorrow also, and then this particular topic will be finished. So I think one class, I thought that today will be, I'll complete it, but somehow we'll have to take one more class. Fine, but understand, is that clear? Please let me know from the comments so that I will move forward then. Or if that's not clear, then I will have to again explain you this. Is everybody hearing it or not hearing it? I don't know. Please let me know if you're getting this concept. If the value comes infinite, then it means divergent, right? Yes, indeed. So if your value is coming as infinite, then then it is divergent. If there is a finite value to it, then you can say that this is convergent. Okay, so basically what we are doing, we are replacing this summation by an integration. So I'm not going into the derivation part, but just for physics people, you should just understand that if I have to evaluate this, why not integrate this out? Okay, because after all, variable summing is integral, right? So just understand that way. And usually in maths class, I actually derive this particular thing, but right now I'm not deriving it. Just understand summation 1 upon n is replaced by summation fn, and I am thinking about this f of n, how this f of n behaves. Let me write that f of x is 1 over x. Simply x is replaced by n, then this will become this structure. Understand how does this thing behave. So if this particular integration 1 to infinity f of x dx is convergent, then good. If it is not, then this is divergent. So summation 1 upon n is divergent. Now what do you think about other cases when p is not equal to 1? So if p is not equal to 1, then this integration would be this, from 1 to infinity. And this integration, I think it's easier to find that this would be 1 minus of p divided by 1 minus of p, where p is not equal to 1. Okay, 1 to infinity. Now if p lies between 0 and 1, if p lies between 0 and 1, x की power 1 minus p would go towards infinity as upper limit is infinity, isn't it? Since upper limit is infinity, so what, and obviously are you getting the point? So since upper limit is infinity, if you place upper limit here, it will become infinity if p is lying between 0 and 1, because if p is lying between 0 and 1, there would be some positive power left in the exponent. Now if p is greater than 1, so clearly for p lying between 0 and 1 also, this integral is going towards infinity. It implies for p lying between 0 and 1, and even including 1, summation n ki power minus p, n varying from 1 to infinity, can be written as a divergent series. Okay. And what if p is greater than 1? What if p is greater than 1? Then if p is greater than 1, if you replace infinity here, I mean if you put infinity here, if p is greater than 1, then this would give you a negative power, because if p is greater than 1, then you are having a negative power over x. So 1 over x tending to infinity, this will give you 0, minus 1, so this will give you 1 upon p minus 1. So you'll get a finite answer here. So you can write that summation n equals to 1 to infinity n ki power minus p, which is nothing but your Riemann zeta function, is what? It is convergent only if p is greater than 1. This is what we have found from the comparison test also. This is what we have found from the Cauchy's integral test also. I hope it is clear. Now we'll move to two different tests, and in mathematics it is often contested that the ratio test is less powerful than the root test. So there are two tests, and I'll give you instances where we have to apply. So probably I'll take one more class tomorrow just for problems. Okay, so we'll do tomorrow problems. Today let us first cover all the tests. So another test is called as the Day-Lambert's ratio test. So what is Day-Lambert's ratio test? Let me help you with this. So let summation n be a positive term series. Let summation n be a positive term series. PT means positive term series, and this particular series will be convergent if limit n tends to infinity, an plus 1 upon an is equals to some r, and it is less than 1. Okay, so if it is less than 1 and greater than 0, because since it is a positive term series, then I'll say that my series is convergent. And if this limit r is greater than 1, then it is divergent. The worst part is when r is equal to 1, then the test becomes inconclusive. That we cannot think what to do, what not to do. Then we'll have to resort to some other test or some other reasoning. Okay, so if r equals to 1, then the test becomes inconclusive. And similarly, there is another test which is called as the root test. This is called as the Cauchy's root test. This is called as the Cauchy's root test. And what does it say? It says that let an be a positive, let an be greater than equal to 0, and if summation n convergence and divergence is being looked at, just find this limit n tends to infinity, an mod raised to power 1 over n. If this is equals to some r and r is less than 1, then this is convergent. If r is greater than 1, then this is divergent. And if r is equals to 1, it is inconclusive. In mathematics textbooks, most often it is written and it is proven that Cauchy's root test is more powerful than the Day-Lambert's ratio test. So it may happen that probably Day-Lambert's ratio test may not give you an answer, but Cauchy's root test gives you an answer. But again, this you can only do in certain cases. In certain cases, I'll let you know, where you have, let's say, power n square. So if you have something power n square, let's say there is some term xn and then you have power of n square, then it is not fruitful to replace it by n plus 1, because if you do n plus 1 ka square and then you try to write this will become very, very difficult. So it's better to take power 1 over n. So whenever you have such things where you have power of n square, try to use root test instead of using ratio test. So this is one of the advice that I have for you. Now let us do a few questions, and then we'll think of some different. One more test also you should remember. I'll give you that particular test also. That is called as a Leibniz test, and that is very specifically used for alternating series. That is very specifically used for the alternating series. So if you have an alternating series, by alternating I mean one positive, another negative, one positive, another negative. So if you get a series in which uh, one term is positive, the another term is negative alternatively, then this particular series is called as the Leibniz. This particular series is called as an alternating series. This particular series is called as an alternating series. So let me just help you with the test, and then we'll do all these tests together. So I'll help you with all these tests. Don't worry. So another test, all these four tests, if you remember, and this additionally one more test I'm writing, Leibniz test. So let's say if you have this series summation, let's say this is your summation minus 1 raised to power n and an. If this is the series and specifically an, here it is obviously greater than equal to 0, it is accompanied by minus 1. So what will happen? It will happen that one term would be positive, another term would be negative, one term would be positive, another term would be negative. And if this is the case, let me take greater than 0 only. If this is the case, just find two things. The first thing that you should think is that whether limit an is 0 or not, and also think that an is a decreasing sequence or not. If an is decreasing sequence, and limit an is 0, then summation minus 1 raised to power n an is a convergent series. It is a convergent series. One of the most important example is minus 1 raised to power n 1 upon n. So this particular series is convergent. Why this particular series is convergent? Because 1 upon n is a decreasing sequence. Isn't it? You can yourself check it. What would be the terms? Terms would be 1, 1 by 2, 1 by 3, 1 by 4. And limit 1 upon n is going towards 0. So clearly both of the statements qualify. If this is the case, then this is convergent, and this is what you refer to as Leibniz test. So, however, the absolute of it is not convergent. If you take an absolute value of it, you will get 1 over n. 1 over n is not convergent. But the alternating counterpart of your harmonic series is convergent. Is that clear or not clear? Please let me know. If this is clear, then I can move to the I can move to other questions, and then we'll see how many of you are following the things. Please let me know through comments. I think there are only 2 people who are watching this lecture right now. Please let me know if there is an issue that you are getting. Okay, till now I think everything is clear, or not clear. Or should I move to the questions? I'll give one more day to this particular topic. Don't worry. So tomorrow also I'm going to do questions. Today I'm going to do a few more, and then we'll meet tomorrow. Problems on infinite series. Okay, and most of the questions that I'm going to give you are going to be questions that are of more importance in physics only. So let us first test the convergence of n upon 2 की power n. Let us first test the convergence of n upon 2 की power n. How to find this particular thing? N upon 2 की power n. Okay, so n upon 2 की power n. Let us first use ratio test. Let us first use the ratio test. This is an important test. Always remember, whenever you have these linear powers, ratio test is very powerful here. So just try to find limit n tends to infinity. An is what? An is simply n upon 2 की power n. Just try to find an plus 1 divided by an. What would be the limit? This would be n plus 1 divided by 2 की power of n plus 1 into 2 की power of n into n. So you will get simply 1 plus 1 upon n, and then you have this 1 upon 2. N tends to infinity, this would go towards 0, and this is 1 upon 2. 1 upon 2 is clearly less than 1. So limit n tends to infinity, an plus 1 upon an is less than 1. It implies that summation an is convergent by ratio test. This is by ratio test. I hope it is clear. Now let us move to one of the very slowly decaying diverging series. So let us take a slowly decaying. Is that clear? Let us take one more case of a slow, you can say a harmonic, even more slow harmonic series. So what I've done, instead of doing 1 upon n, I'm doing summation n into log of n, and I'm not starting from 0, I'm not starting from 1, rather I'm starting from 2, because log of 1 is 0. So I've started from 2. What do you think about this series? Whether this would be a convergent series or a divergent series? Whether this would be a convergent series or a divergent series. Let us see. What do you think about this? Only one is there or some? Okay, Anshul is there. Okay, Anshul, what do you think about this series? So what I would do, because this is slightly complicated, so what I would do, I would simply use, actually see, it is quite easy to see that log of x is an increasing function. Log of x is an increasing function. So if you increase your n, this is going to increase. And if I do 1 over it, so I can say that 1 upon n into ln n is a decreasing sequence. Why it is a decreasing sequence? Because if you increase n, uh, like I know that if n2 is greater than n1, then log of n2 is greater than log of n1, and n2, if I multiply both sides, if I multiply this n2 here and if I multiply n1 here, so clearly I can say that this particular part would be greater than this particular part, and if I see 1 upon n2 ln n2, this will be less than 1 upon n1 ln n1. So clearly this particular sequence 1 upon n into ln n is a decreasing sequence, and all the more if I just try to use one integration. Instead of doing this, I just want to do this. So I'll use this integration from 2 to infinity, obviously not 1 from infinity, because at 1 there would be a singularity, because at 1 log 1 is 0. So if I do this integration, this I will get log of x. This is quite easy to do, because log of x, let it be t, then 1 upon x dx would be dt, and I'm doing it from 2 to infinity. This would diverge towards infinity. So clearly summation 1 upon n ln n is a divergent series. I hope it is clear or not clear. Also, I think you can, if I want to apply a comparison test, probably I may apply. So in series you can leave some terms also. In series you can leave some terms also. Let's say I'm leaving this term. Instead of 2, I'm writing it from 3. Because after all, if this infinite part is convergent, then adding a few terms, subtracting a few terms in the series will not matter. So what I'm going to write, let me just think, if that's working, then it's fine. Otherwise, I'll change the root. So log n is always greater than 1. Log n is always greater than 1 for all n greater than equal to e. So instead of e, I'm going to write n greater than equal to 3, because e is around 2.7183. The next natural number is 3. So I can write for all n greater than equal to 3, log n would be greater than 1. And if I write this way, so I think this is not making sense. This is not making sense. Okay. I thought I would be able to somehow do it, but it's not making sense. Okay. So the best strategy here would be to use the Cauchy's integral test, because otherwise the series here would, if I just multiply it by, what I am doing is, see, log n is greater than 1 for all n greater than equal to 3. If I do 1 upon log n, 1 upon log n, sorry, this is not the case. So 1 upon log n will be less than 1, and if I write 1 upon n both sides, so this is divergent. But nothing can be said. If this is divergent, then I cannot say this is divergent. However, if something comes here, and if I can claim that that is divergent, then I can say this is divergent. So rather, I think this would be a better thing to do. And there is another test called as Cauchy's, if I correctly remember, that is called as condensation test. I have not taught you, and I'm not going to teach you that also. That is absolutely fine. Just remember this test. This is more than sufficient. Whatever test I'm giving you, this is more than sufficient when it comes to your exam. Okay. So a few more questions I'm going to give you, and let us see how many of these questions you can do, and then we'll move to the different other topics. Just give me a minute. Questions. Okay, a few more questions I wanted to give, and if those questions you can do, then I think that will be more than sufficient for your exam. However, I'm going to take one more class tomorrow, so that this does not remain in your head that you have not done this topic. Usually, TFR and JEST exams have these questions. You'll find that most often JAM or JEST, some like these exams only, you'll find these questions. Okay. So one of the question has been asked in JEST exam only. So let us do that question first. I think this is not even related to your ratio test or anything, but let us do. Summation n equals to 1 to 99. This is asked in JEST exam. Summation 1 to 99, 1 upon root over m plus 1 plus root over m. How would you do this question? How would you do this question? So the better strategy to do this question would be to actually rationalize it. So best strategy is rationalize. So if I rationalize it by root over m plus 1 minus root over m, and if I divide it by m plus 1 minus of m, then what I'll get, this gets cancelled, and here I have root over, so this is m equals to 1 to 99. So what I'll get, I will simply get root over 2 minus root over 1 plus root over 3 minus root over 2 plus root over 4 minus root over 3 plus so on and so forth. If I use the last term 98, so this will be root over 99 minus root over 98, and then plus root over, if I do this 99, this would be 100 minus root over 99. So what will happen? Please remember, in each of the bracket, the former part is being cut by the next bracket's latter part. In each of the bracket, the former part is being cut by the next bracket's latter part. In each of the bracket, the former part is being cut by the latter part. In each of the bracket, the former part is being cut by the latter part. This is latter, it would have been cut by some former part. This is former part of this bracket. You do not have any other bracket outside of this. So the answer would be simply root over 100 minus root over 1. So this will be answer 99. Sorry, 9. Sorry. Root over 10 is root over 100 is root over 100 is simply root over 100 is simply 10. 10 minus 1 is 9. I hope it is clear. I hope it is clear. Okay. So I think it is enough for today. Tomorrow I'm going to do only questions on infinite series. Please revise whatever has been done. Don't think about any book from where you are going to do this, from where not you are going to do this. Just focus on whatever I have taught you today. Once you do this, then I'm going to do enough questions tomorrow. These are like in the, you can say, chapter wise only, like you can say test wise. Test wise, I'm going to give you some questions. That this is a question for ratio test, this is a question for root test, and once you're done with all these tests, then some random questions, and then I think it would be more than sufficient. Don't waste much time into this. This is just basic starting. That's why I've taken up this topic. I hope to meet you tomorrow. Till then, take care. Bye bye.